Right. Hopefully this works, and if it doesn't work on the fourth attempt, then quite frankly, I give up. But basically, with modelling assumptions, when you're looking at year 12, well, in fact, all of year 12 and 13, but in particular, there's a chapter 8, which explains it all on Pearson Active Learn. But in my opinion, there are sort of four main things which you need to know. So you've got particles. Now, whenever something's you said it's modeled as a particle, what that means is you can actually ignore certain things. And I'm using this racing car as an example. So if you've got this race car, what you've got is, imagine if it's driving on the road, it will have a lot of air resistance. And obviously it's designed in a way so that the air resistance sort of brushes off or sort of goes into the vents here and then goes downwards to help with the car's aerodynamics. So if you can see, it's got that pointy face. But with if you're modeling it in mechanics, it will look like that. Great car. And with that, it's got no air resistance. So if that particle is moving in the right-hand direction, it's got no air resistance. So it's just moving without any resistance. Similarly, if it's actually falling downwards, again, it's got no resistance. So it's still under gravity. The gravity's working, but no air resistance of pushing it back up, or likewise with the pushing it back up, or likewise with the car moving across, it's not trying to push it back. So whenever it's modeled as a particle, the assumption is that there's no air resistance or any other resistance working on it. But also, a really big point is the weight or the mass is at one way at a very specific point. So obviously with our racing car, it's obviously got different weights spread throughout. With a particle, imagine if it's absolutely tiny, and therefore the weight of it or the mass of it is only pressurized on a singular point. Now the next is going to be a light and extensible string. So if we have our two cars here, and if pulling on a light and extensible string, what that basically means is, as the AA car is pulling the Corsa because it's broken, what that means is that string won't get any longer. It stays at a fixed length. And what that means is the tension going either way remains the same throughout. So imagine if you've got, sometimes it's said as a rod. So a rod, the tension's working exactly the same. But imagine if you've got a really thick rope and it doesn't sort of extend, unlike what a bungee cord, if you had a bungee cord or a rubber band, as you pull it, the tension is changing all the time. Whereas with a light and extensible string, it means it stays exactly the same. Now with pulleys, what we're saying with the pulley is that it's acting, imagine that's the table, and then this is the table leg here. What we're saying with this pulley here, and one of the words that they use is smooth. And what that means is that there's no friction working on it. And that's the same with this table. This table we're going to presume is smooth. The reason why we're going to presume it's smooth is because there's no friction working on it, which means there's no friction working on it. But what it means by why we presume that it's smooth is because there's no lines drawn here. As soon as there's lines drawn there, that means it's got friction. It's a rough surface. So that's a later question which you'll come into. But the modelling assumption is that with a pulley or a smooth road, table, whatever, there's no friction acting on it. So basically means that the forces, imagine if this weighed 10 kg and this weighed 2 kg, as the pulley's released, i.e. the stopper's gone, this 10 kilograms would move downwards, and then this 2 kilograms would move in the right-hand direction. And if it's got a light and extensible string, both of them will be moving at the rate, because obviously that string can't get any bigger, any longer. So they're both moving in the same direct. Well, they're both moving in the way that you would think. And this 10 kilograms going down the right, and the 2 kilograms right. But because it's smooth and it's a smooth pulley, there's no other forces acting on it. Okay, obviously with this 10 kilograms, you've got 10 G, so you would be able to work out the acceleration. The last thing that you'll need is about uniform versus non-uniform beam. Really, it's all about the word uniform and non-uniform. So if we take our racing car, or let's stick with the beam. If I've got a beam like that, and let's say it's a massive plank of wood, it weighs 50 kilograms. What we're essentially saying, when it's uniform, it means all of the weight is acting is spread out evenly. And when it's spread out evenly, you've got your center of mass. Okay, so essentially, the way we model that is by putting it in the middle. So if it weighed 50 kilograms, we've got 50 G working down right in the middle of that beam. Whereas if it's non-uniform, basically means it could be really thick at this end and then gradually gets thinner at that end. So the weight could actually be working in this area here, instead of in the middle. And that's the difference between uniform and non-uniform. Uniform means the weight is evenly distributed, so we can say it acts at one point, which is in the middle. Whereas non-uniform means that it's still got the same weight, but it won't be in the middle because it may be at one side or the other. In the exam, all you need to do is say it's acting on one, it's not acting down the middle, it's acting at point X, for example. Those are absolutely the main modeling assumptions. In the book, on virtually like the second page or something like that, 8C, I think it is. Sorry, second chapter. It's got really good definitions for all of them. I don't think you really need all of them. I think these are the main ones. So if you understand that particles are where you don't have any air resistance or anything like that, and also the weight's acting at a singular point. Light inextensible string, tension remains the same and it doesn't get any longer. Tension same as the main one. That's an example of the pulley, but smooth is where there's no friction. Rough is where there is friction. And then uniform versus non-uniform beams. Uniform beam, it's acting at the point of the beam. And then non-uniform, it's acting not at the center of the beam. The weight is acting not at the center. And that is pretty much it. Any questions, any issues with that one? Obviously, just let me know. But hopefully that answers everything. Perfect. Right, let me pause this then.